Unlock the secrets of matrix transformation, similarity, and unitarity magic revealed. Discover how these powerful tools preserve the essence of linear algebra and revolutionize your understanding of matrices. So in our problem A.16, show that similarity preserves matrix multiplication, that is, if AE/BE equals CE, then AF/BF equals CF. Similarity does not, in general, preserve symmetry, reality, or hermicity. Show, however, that if S is unitary and HE is Hermitian, then HF is also Hermitian. Show that S carries an orthogonal basis into another orthogonal basis if and only if it is unitary. Very important. Let's review some terms. So for something to be Hermitian, we need that its dagger or adjoint conjugate, however terms you want to use, conjugate transpose, the likes. The dagger equals the original matrix. For something to be unitary, we need the dagger to be equal to its inverse. And for the similarity transform, TF is equal to some transformation matrix S times the original matrix TE times the S inverse. We've seen something like that before in the quantum mechanics book with the unitary matrix or unitary transform. Finally, we have a vector transform where we see that AF is equal to SAE, very important for us. And then finally, the orthonormal condition for any vectors alpha beta, we're able to take the conjugate transpose and dot it with this. Again, if we think about this in terms of like I hat, J hat, K hat, we know that we can get a dot product out of these if they're orthogonal or orthonormal because all the other cross products will cancel out. Well, cross terms rather, not cross products. So by using unitary transformations to describe time evolution, quantum mechanics ensures that the fundamental principles of quantum theory are respected throughout the dynamic processes of quantum systems. So these transformations are used in real world and not just some landscape of linear algebra. I promise these definitely come up quite a bit. So in our first stop in this process, we're looking at the preservation of matrix multiplication. And this problem demonstrates two key concepts of linear algebra: the preservation of this matrix multiplication under similarity transforms and the preservation of Hermicity under the unitary transforms. Let's see what we have to do though. So for this, let's consider the similarity transform where we have TF, the new matrix, is equal to the transform matrix, TE, and the inverse of the transform matrix. Here, S is an invertible matrix, otherwise this can't work. So we aim to prove that this transformation preserves matrix multiplication. And to show that the similarity preserves matrix multiplication, we need to consider, well, if I have two matrices that are transformed, such that AF is equal to SAE S inverse, similarly for B, then their product is equal to CF, given that AE times BE equals CE. Okay, so pretty straightforward. All we have to do is multiply together these definitions of AF and BF. So we see that AF times BF, we have the SAE S inverse, SBE S inverse multiply together. Use the associativity that we know from vector space axioms and look at the inner two matrix multiplications. Now the S inverse and S, since S is invertible, non-singular so to speak, that equals the identity. And from the identity, whether we left multiply or right multiply, we're good to go. We get the restoration of the matrix we're multiplying with. So we end up with just AE, BE in the middle. But again, associativity, we can look at AEB as the product first. But because of our statement of the matrix product, that gives us CE. Then CE is in the middle of S and S inverse. So that is the definition of the transform. So we get out the CF matrix that we wanted and prove that preservation of multiplication does indeed occur. So this equality demonstrates that the product of transformed matrices is equivalent to the transformation of the product of the original matrices. Thus, the preservation operation of multiplication under the similarity transforms holds and we're good to go. Very important. Now, a little more complicated is the preservation of hermiticity. So now let's examine how unitary transforms preserve hermiticity. Now note that a similarity transform and a unitary transform are the same thing, but the matrix has to be unitary as well as invertible. So here, a matrix H is considered Hermitian if H dagger, where H dagger is the conjugate transpose, is equal to H. So given a unitary matrix S, where S dagger equals S inverse, from the statement of S dagger S equals S dagger equals I, and a Hermitian matrix HE, we can show that HF is equal to S, HE S inverse is also Hermitian. Again, we see that this is a similarity transform, but now we're also invoking that S be unitary based on this statement here, and that makes it a unitary transformation. So by using our definitions, if we have the similarity transform here, which we're now going to cascade to unitary transform, and we decide to take the dagger since that's the hallmark of the Hermitian property, we know that the dagger of the product is equal to the product of the daggers, but in reverse order. Okay, thank you, transpose property. And then we see here that color coding it, we reverse the order, but now that we know we're given the conditions that S is also unitary and HE is Hermitian, we can see that this inverse gets to a dagger. This dagger with the matrix goes back to the matrix thanks to being Hermitian. This dagger now goes to the inverse thanks to being unitary, so we all work together. Now note that dagger on dagger undoes the dagger, right? So it's kind of nice there. What we say here is that if I take the conjugate of something and I take the conjugate again, the conjugates undo each other. If I take the transpose again, I'm switching row to column, and then I'm switching column to row, so I restore the original matrix, so that's why we see just S here alone. And now we see that we're in the same form that we need, S, HES inverse, right, from the transform definition, so that equals HF itself. As we can see, based on these two given parameters, we get that HF dagger is equal to HF. So this proof demonstrates that the transformed matrix HF satisfies the hermiticity condition, thus preserving this important property under the unitary transform. And again, just for reference, the unitary that we saw in chapter 6 of this book and chapter 7 of the quantum mechanics book was U dagger, has the same form here, U dagger, but we see that U has to be unitary, so S inverse equals S dagger, which is what we see here, so that's why we just say it's a unitary transform. The resulting expression owes its result to the unitarity of S. Clearly we see that without this, we're not able to switch this inverse to a dagger and undo it, nor are we able to switch this dagger to an inverse. So this ensures that the proper form is maintained and we are good to go. Now, as far as the preservation of orthonormality is concerned, the necessity for S to be a unitary matrix becomes apparent when we are examining the orthonormality condition in the transform bases. So in an orthonormal basis, we're told that the inner product of alpha beta is equal to A dagger B, okay? This comes out to a number, and again, there's another way to look at this, which we'll cover next, but let's go with the definitions given in the appendix. So this is what we're looking at. And so if we're looking at this definition for the orthonormal bases from the inner product perspective, for a transform basis such that Fi, where we're indexing to I, to remain orthonormal, we must have that alpha beta is equal to AF dagger BF. So this has to hold. So given that AF is equal to the transformation times the vector, transformation matrix times the vector, that gives us the new frame. If I take the dagger of this statement here, dagger, dagger, we know that the dagger of a product is the product of the daggers in reverse order. So that's why we see here. Now, since we don't have a dagger on the B, we just have BF, the final, is equal to the transformation matrix times the B vector. As a result, when we take the inner product and look at this, we see that we have AF dagger BF, but sub in this definition here, use associativity, and we see that in order for S dagger S to go away, to restore the original statement, this has to be unitary. Okay, so this equals the original orthonormal bases expression, alpha beta equals AE dagger BE, if and only if, because there is no way around it, S dagger S equals I, which is the definition of unitary. Now, this is pretty straightforward, but we see that the necessity for transformations and unitarity go one-to-one because we want to preserve most of the things. And in physics, we want to preserve the values that we get, say, energy, regardless of how I try to frame my coordinates to maintain an easier measurement, per se. So the energy of the system doesn't necessarily change just because I change the way I try to observe it. And that's what we're trying to get across with these unitary things and why unitary transformations are very important, especially to quantum mechanics and the field theories. But there is another way to look at this section of the proof. So the preservation of orthonormality, which is probably one that's a little more linear algebra heavy, but probably one that's insightful too, based on our knowledge of what orthonormal means with the Kronecker delta. So in another perspective, the requirement for S to be unitary is crucial when considering orthonormality in the transform bases. In an orthonormal basis, we have that the inner product alpha I alpha j is equal to the Kronecker delta ij. Okay, so we only have something there normal because we're looking at the bases themselves. So I hat to I hat gives us 1, I hat to j hat gives us 0 because there's no overlap. Okay, so for transform bases where we have ai prime is equal to the transformation acting on the old vector to remain orthonormal, we must have that A prime, AI prime, AJ prime, which is equal to the transformations. Remember the properties of Braun and Ketz, where I can take this, take the dagger of it to put it to the other side. Hence, I end up with S dagger, S in the inside here of the inner product. And we need this statement to equal this. But this only holds if and only if S dagger S equals I, because then we have the replenishment of alpha I alpha j, which is the definition of a unitary matrix. So once again, we see two perspectives, both illustrating the same thing, but both crucially important to show that the necessity for unitarity is very much needed. So in conclusion, these properties of similarity and unitary transformations are fundamental in various areas of physics and mathematics, particularly in quantum mechanics and linear algebra, where they play a crucial role in preserving important physical and mathematical structures under coordinate transformations. They very much are important. Okay, so fairly quick video, but very important. These transformations tend to be a lull point for many students, myself included, when I first saw them. Even now, as I'm brushing up on them, when you want to talk about field theories and things like that, or astrophysics and, general relativity, being able to transform is very, very important. The transformation matrices play a huge role in that, so be aware that these will come up time and time again. If this video got you thinking, imagine what's coming next. Subscribe and join our community for weekly insights into the world of physics. There is so much more to uncover, and I'd love to have you along for the journey. I also just want to take a moment to thank my incredible Patreon supporters. Your support is truly the backbone of this channel. It's because of you that I'm able to keep creating these videos and diving deep into the fascinating world of physics with everyone. Your contributions make a real difference in helping me bring these concepts to life, and I'm so grateful to each of you for believing in this journey. And if anyone else is interested in supporting the channel and joining our Patreon community, you can check out the link in the description below. Together, we keep exploring the wonders of science and discovering even more amazing things. As always, thank you for watching, and until next time, stay curious.